Hello, everyone. I'm Elad Verbin from Berlin Innovation Ventures. I'll introduce myself in a bit, but first of all, we're going to talk about privacy on the blockchain. And in particular, I'm going to tell you how privacy on the blockchain is entirely, completely broken in a way that we should all know about. So suppose you use your Bitcoin wallet to buy a pizza, and you have the pizza delivered to you. And then you use the same wallet to buy, or the same address to buy a bag of weed. Now, the person who bought the pizza also knows that you're the same person who bought the weed, which means that you can be slowly unmasked if you do more and more operations, you can be slowly unmasked. In general, this is not a theoretical possibility, this is a real thing. So blockchain privacy is extremely broken. There are companies that are experts in de-anonymizing blockchain users or Bitcoin users, and there's even a Coursera course about how to do this so that everyone can learn how to de-anonymize Bitcoin users. And that's not surprising because blockchain privacy is broken on purpose. We've been promising Bitcoin as the anonymous coin, as the anonymous transaction mechanism for many years, and it's either lying or by omission or something like this, but it was never anonymous. Bitcoin is pseudonymous, meaning you are represented by your public key, or what is known as your Bitcoin address, but you're never actually anonymous, and you can be traced like this. They tell Bitcoin users, when Bitcoin users ask, they tell them, don't use the same wallet twice, or the same address twice. Well, you have to use the same address twice, once to receive money and once to pay, and you can do all kinds of fancy things like mixing networks and so on, but the core property of Bitcoin is that it can never, I believe, be truly anonymous. And in general, blockchains are not private at all. They were in fact designed to be extremely transparent. They're the most transparent thing you can imagine. When I transfer 2 Bitcoins to Satoshi Nakamoto, this is basically written on the chain. Elad Verbin transfers 2 Bitcoin to Satoshi Nakamoto, and that's on purpose so that everyone is accountable. Because once I write that, I send this transaction and sign it and publish it to the chain, everyone in the world has, every miner in the world has a copy of the complete chain and checks that I really had the 2 Bitcoins I'm going to spend and that I'm really me and so on. Every single miner checks this stuff, and that's how we achieve accountability on the blockchain. So blockchains are transparent in order to achieve accountability. The problem is that transparency is really bad for privacy, because once everything is published on the chain, then everyone can see who's paying anyone else. This is not the same as your bank account, right? When I transfer $2,000 to Satoshi Nakamoto, the only people that know that this transfer ever happened is me, Satoshi, and the bank. And that's all. So banks are very, very private in that sense. In fact, they are bound by laws that make them private in this sense. While Bitcoin is very, very unprivate or very transparent in that sense. So the really core question is, can we maximize accountability and still minimize transparency or maximize privacy? And the answer is yes. And private computation, which is going to be what I'm going to tell you about in this talk, is exactly the cryptographic toolbox to achieve this, right? To achieve maximum accountability without needing any transparency. The kind of cryptographic curse words we're going to talk about are stuff that was cryptographic science that was invented in the 90s by people like Shafi Goldwasser and Silvio Micali, Andy Yao and others. And these are tools like zero-knowledge proof, secure multi-party computation that we'll describe in depth, homomorphic encryption, and so on. So this problem, the particular problem of the lack of privacy on Bitcoin, was already solved by projects like Zcash and others that employ really high caliber cryptographers to solve this problem. But I'm going to tell you that this privacy or lack of privacy problem was not solved in many other instances. So there are many privacy coins, as they're called, out there, and some of them are very, very good and very privacy preserving. Let me tell you, though, about some applications that we don't yet have the complete technological solutions for. So for example, suppose I'm a smart data scientist and you're a smart pharma corporation. You have a lot of patient data and DNA that you can't share with anyone, legally, regulatorily, it's your intellectual property and so on. I have algorithms, very smart algorithms that I don't want to share with anyone. They're my IP, but we still want to apply my algorithms on your data in order to find clever new drugs. How will we do that? Well, the kind of techniques I'll show you allow us to do these things, so we can apply my algorithm on the data that you have without me telling you anything about the algorithm and you telling me anything about the patient data, yet we get all the benefits of computing them together and we both learn the solution. Another application, you can think of Tinder. Suppose we both swipe, I see on Tinder, I swipe right and you swipe left. I don't want you to know that I swiped right, but if you do this on the blockchain has maximum accountability, minimum privacy, the swipe direction is posted on the chain. What we would like to do is compute something together. We want to compute the end function so that we only learn that we're a match if we both swipe right. And if one of us swipes left, all any of us learn is that the result is no match. Okay? Private computation allows us to do that by allowing us to compute things privately between us. Voting is another approach. The way to achieve private voting without and still know who won is using private computation. You collect all the votes and you choose the winner, but you do that while preserving the privacy of all of the participants. And finally, we already saw sending money is another approach like this, where we want to do all of the accounting that Bitcoin would do, but keeping everyone's privacy. All of these are cryptographically provable privacy. So these use the techniques of provable cryptography in order to ensure privacy. And it's very important to say this is about private computation. So it's not about communication, which is kind of a solved task. If you think of SSH, of the way you communicate with internet servers, everything is very privately communicated. But it's not about checking that my balance is still high enough to send it to Bitcoin. It's not about checking that the recipient, really knows that, or that I really signed the message and so on. So this kind of cryptographic toolboxes allow us to do private computation, which is a much harder task than private communication, Okay, so what are we going to talk about? We're going to talk about why privacy on the blockchain matters. We're going to talk a little bit about how the cryptography works, and then talk a little bit about applications. So why privacy matters? As we said already, privacy on the blockchain is broken. That's really important. But second of all, private computation is really necessary for the Web3, right? If we want to do Uber on the blockchain, eBay on the blockchain, and so on, we really need privacy to be maintained, and so complete transparency is very unfeasible. So to allow all of these future applications, we really need to boost privacy. And third of all, if you're a cold-hearted cynic that doesn't care at all about the privacy of individuals, you should still care about these toolboxes. Because when there's more privacy, people are willing to share more. Businesses, for example, are sharing almost nothing today on the blockchain, specifically because there's no privacy. If you allow them privacy, they'll share much more, and you'll get much more business value. Right? So the buzzword zoo. So we are talking about this set of techniques that was invented by this kind of people. Look how they're dressed, as opposed to private communication that's a different toolbox, much older, that was invented by this kind of people. And then to create a full stack of privacy tools, you need also other techniques that I will not talk about, like Tor, hiding your IP, differential privacy, and so on, to create an entire stack. So in this talk, we're only going to talk about this kind of techniques. Okay, so what is secure multi-party computation, which is the nicest, strongest cryptographic private computation tool that I know? It is when n players want to compute a function together. In this case, they're trying to decide who the winner is in a bid, in an auction. So each of them bids, and the goal is to just find out who bid the highest without divulging their bids to each other, right? So in a really closed envelope auction, this is very easy. Some trusted entity gets all of the envelopes, opens them, and just publishes that this player won by bidding 8, and that's the highest. And if we have a trusted entity, that's fine. But if we don't have a trusted entity, what do? We do secure multi-party computation. Each of the players has their bid, and each player may only learn their own input, which they already know, and the output, who won and how much they bid. So, and this should be true even if some players collude and attack the protocol. The protocol might not finish, and that's fine, but if it does, but regardless of whether it finishes, we want the privacy to be maintained. And the amazing thing is that this can be done, this task can be achieved for any function f that you'd like. This is magic. Not only for sum or for bidding or for anything, but literally for any function. This was proved by Andy Yao in 1982 and was improved gradually ever since in terms of efficiency and so on. So under some cryptographic assumptions, this can be done. And now we're going to talk about how is this possible and what to do with it. So the way you should think about private computation is the following. It's a decentralization mechanism. You imagine something that can be done with a trusted judge jury, such as resolving an auction. So Alice sends her input, Bob sends his input, Judge Judy computes and returns to them. So you see that Alice only learned her input and the output. And what this result of Yao shows is that you can simulate this simple protocol by a protocol that they just run between them without Judge Judy. So that's what we mean when we say decentralization. It's removing Judge Judy but keeping all of the good properties. Okay, and the way, let's keep that and talk about applications maybe. So the first applications of this secure multi-party computation was in sugar beet auctions in Denmark. This is when sugar beet farmers want to actually sell the rights to grow sugar beet to each other, but they don't want to say how much they're willing to sell them for or buy them for. So they sent this, they encrypted their bits and they sent them to a central server encrypted, and the central server did stuff on encrypted data and resolved the auction. This involves game theory and cryptography. And since then, this became a very prominent use of secure multi-party computation for corporations. So if you're a big business, you have access for this technology for a long time already. And now we're starting to allow this for small businesses. So if you're a small medical company, pharma, we can break data silos, and these companies, Ocean and OpenMind together, are working to do that. We can open data silos and compute on the data that is stored, for example, in in auto manufacturers. We can add value to this data and so on by using this kind of techniques. And in the future, I hope that we'll have something like algorithmic redistribution of wealth. So, for example, right now, the way that redistribution of wealth or taxation works is using algorithms that are rule-based. So very, very simplistic, because they have to be agreed upon by this kind of people and filled upon by us at home, right? But in the future, maybe, but in the for-profit sector, this is not the case at all. Amazon is digging every little cent it can get from all of its users. So clearly the private market is very efficient in optimizing processes, economic processes, and the public market is the public nation-state system is very inefficient. And I hope that in the future, we're going to have a smart combination of algorithms like that optimize economic systems, mechanism design that encourages all of us to really say what we need and how much we can give, economics like public policy to say what it is we're optimizing for, but also cryptography and secure multi-party computation for allowing to keep our privacy and still maintain accountability while resolving this algorithmic redistribution of wealth. So that's a future use case I'm hoping for. And finally, will people trust this thing? Well, when we get on a plane, who would think that a metal in the sky would actually fly? Well, we get used to it. So when I pitch zero knowledge and secure multi-party computation to people, they say, we don't know what you're talking about. This doesn't make any sense that this would exist in the real world, but it does. And people will gradually get used to it, just like they got used to putting their credit card online. So to summarize, I have shown you the field of private computation, which is a cryptographic toolbox that didn't exist in the 70s. It's not the same as private communication, but exists now and is quickly coming to market. This will open a massive design space of applications, of decentralized applications and others in the next 10 years. And finally, this more privacy will actually allow more collaboration, and you're welcome to Google. I gave a talk specifically about collaboration technologies that's available online that focuses on the more what happens when you really when you really can maintain privacy, what collaborations get unlocked. So thank you very much.